projections was saying that let's find a projection that's interesting. Okay, let's stick with the original variates, whether we did Zen plots or we did the navigation graphs. We're staying on the original variates and following those projections, the original variates. In doing a search over all p choose 2 possible combinations of variates and finding the most interesting ones. Well, another way to proceed is to think about actually reducing the dimensionality in the first place. So if I start with thousands of dimensions, maybe I can reduce it to fewer and then start doing what are the interesting projections on those new axis system. So the most common way of reducing dimensionality is just by projection. Is it possible that the data themselves, think of the data as being in a point cloud in high dimensions, is it possible that that data lies near a smaller dimensional subspace? That is a linear subspace. Okay, so we're going to look at that, and that's going to call principal components analysis. How many people have seen principal components before? Oh, about a third. Okay, so we'll go through this kind of slowly. So you know that if I have any set of vectors, v1 through vk, I can project orthogonally onto that space that is spanned by those vectors just by using that regression, that orthogonal projection operator, right? We've seen that a few times already. And if V is an orthonormal basis, we end up that the projection is just VV transpose. Okay? So the question is, can we find directions? These are just direction vectors, if they're orthonormal. They're orthogonal direction vectors. Can we find projections so that the data, when projected onto that subspace, have particular characteristics? So what we're going to start with, assume that I've got n points in p-dimensional space here and that they're centered, that is, they're all around the origin, so that their average is in fact 0. Okay, and I can denote this X matrix in the same way you denote it in a regression or linear models course, to be an n by p real matrix, where the rows of that matrix are the points in the p-dimensional space, and the columns are the dimensions or variates. Okay. So since it's centered, it's a cloud that's around the origin, and every linear subspace goes through the origin, right? So when I say, is it near any particular subspace? That is, are there directions where there's not much variation in the data? Or are there directions where there's a lot of variation in the data? So can we find something that's very nearly in a subspace? Can we find a subspace that the data are very near to? Okay, everybody got that in the notation? So if we're looking at a simple case where we only have 2 dimensions and the point cloud looks centered like that, we think about, well, yes, they are sitting in a 2D space, so it is in fact a plane that it's living in. It's sitting in a 2-dimensional space, but it's really close to a line. That is, there's hardly anything out here, hardly anything out there. They're pretty close to a line, and a line is a 1-dimensional subspace given by the direction vector that defines a line, right? Okay. So how might we look at this? Well, think about looking for a direction vector A, and what happens when we take any point and project it onto A? It'll have some position, and how close it is to that is measured by this. That's supposed to be an orthogonal projection. That this distance of the point from where it appears in that subspace is a measure of how close that point is to that particular subspace, right? And I know that's a direction vector, so it has length 1. So I can make that precise. A is a direction vector. It's only got one dimension, so I know projecting onto that, that's our V transpose. So it's A transpose. A is a column vector. That's going to be equal to something that's proportional to the direction vector A. Some value WK, where WK is obviously going to be A transpose XK. All right? It's okay to do this on the slides, or would you rather I did this on the blackboard? Let's try the slides, and if you say you're getting lost and the notation has disappeared, just let me know. So I can think about when I project it onto that direction vector, I can think about, well, how long is the projected value? How long is the vector there? So think of every x as like a vector in 2D or space, and then I project it onto, so it has some length. I project it onto the direction A. It now has a length again. And we know that that's a right angle triangle. Okay? So the squared length of that vector is just going to be the square of this constant. Right? So that's its distance from the origin. And if you look at the WK squared, that's going to be if the length of the projection, so that's how far along you are this direction. This is the squared Euclidean length of that. You know what the Euclidean length is. The Euclidean length of a vector y is just squared Euclidean length, is just y transpose y. So you just take this thing, transpose at times itself. You're going to have x transpose A, x transpose the transpose of A times A transpose on the left. And on the right, you're going to have A transpose xk. In the middle, you're going to have A transpose A, which is a unit vector, because that thing is length 1. So this is just that thing there. And the simple trick is that this is a scalar, right? It's a row vector times a column vector. So I could take the transpose of it, no problem. And similarly this, I haven't changed anything. And so this is equivalent to these two scalars, that scalar, etc. Okay? Now that says, if I look at that, that's the squared length of the kth vector projected onto the direction A. So I can ask, is there a direction that maximizes or minimizes that or whatever? Makes that as small as possible or as large as possible. Okay? And I've got n of those. So I've got n of those points. I may think about, well, what about the average of all of these over k equals 1 to n? Look at the average squared length. What's the average squared length onto that direction vector A? And ask, is there a direction that maximizes that or minimizes that? So if it's maximizing it, that means everybody's kind of spread out in this way. If it's minimizing it, there's hardly any change. Okay, you're looking for the direction where there's very little change. So it's kind of a measure of how spread out this data is in any particular direction, in the direction A, because it's centered around the origin. Okay? Everybody with me so far? Good. So I may be interested in the average, or equivalently the total of the squared lengths of the squared lengths of the projections of all of the x vectors onto a particular direction A. That's that sum, which we agreed was the sum of these guys, which we agreed I could rewrite this way. The reason for rewriting it that way is I can now I can factor this and have the A transpose appear on the outside of the sum. A's got nothing to do with the sum, so I've got the sum in the center. Okay? And if you look back at our definition of this X matrix, right, where every row of X was the ith row of X was Xi transpose, little xi transpose. This sum is just simply that. Okay? Make sense? Everybody's good? Any questions? Okay. So, what do I want to do? Well, I want to find a direction vector that maximizes that quantity. It's a function of A, subject to the constraint A transpose A equals 1. You know how to do that. There's a constraint, a simple equality constraint. We handle that with a Lagrange multiplier. So this turns into, what I really want to do is minimize that over A and lambda, lambda being the Lagrange multiplier. Okay? Because when I differentiate that with respect to lambda and set it equal to 0, I'm going to have this must be 0, which enforces this constraint. Okay? So I want to differentiate this. Well, what does it look like? This is a quadratic form. That is, when I think of that as a function of the elements of A, every element in A appears as an AI squared or an AI times an AJ. Okay? So it's quadratic in the A's. Similarly over here, also quadratic. So you know how to differentiate things that are polynomials, right? So you could differentiate a squared term and a linear term and a constant term, right? Ax squared plus bx plus c, if I differentiate that with respect to x, right, I'm going to get 2ax plus b, right? So this is, I'm going to differentiate with respect to a vector. Again, quadratic forms. So it should be just as simple, right? And if you take a quadratic form here like this, quadratic and it's got a linear form, and you differentiate that with respect to z, what do you suppose that should be? So that should be 2az plus b. It is. Okay? So you can differentiate that yourself with that vector every piece and then put it back together again. It'll look like that. So that derivative does in fact look like this. Okay? So now that's a derivative. I need to set it equal to 0 and solve. Back in our system, A was this thing here. Because if you go back, I had A transpose times X transpose X. Was a lambda minus, there's an I in there, right? So X transpose X minus lambda times the identity. I'll put an little a transpose on either side of that, and you'll get this. Okay, and I've got a lambda for this C. So differentiating it and we're setting it to 0 and solving, I've got this system of equations here, right? So in this up here, this is 2. The A is that thing. The Z is this little a. Set it equal to 0. Solving, I have this system of equations. Does that look familiar? Can anybody tell me what the solution A is? The eigenvector. And what is lambda? The eigenvalue. Okay? Here's your definition of eigenvectors and eigenvalues. Scaled so that that A vector is a unit vector. Get yourself a unique lambda. Okay? So the solution there, the direction you're looking for, is it going to be an eigenvector of this X transpose X matrix? Okay? So that thing should look familiar. It's the eigenvector and eigenvalue of a real symmetric matrix X transpose X. And if I want to maximize this, I choose the eigenvector corresponding to the largest eigenvalue. Because I remind you, right, that, let's see, the size of this projection is equal to lambda. So if I want to maximize that, I want the biggest eigenvalue. If I want to minimize it, I want the smallest eigenvalue. Okay. I can proceed then, and I can, if I denote the solution by one of these vectors v, v1, or vp for the smallest one, I can get an orthogonal matrix v. Sorry, to do this, get each in sequence, I'd have to go and say, now I want to choose the second direction, say direction b, that maximizes this quantity subject to the constraint that it's orthogonal to the previous one. We'll end up picking off all of the orthogonal eigenvectors. Okay? So what do I need to do? I need to do an eigen-decomposition of this real symmetric matrix. And we'll call that V d lambda V transpose, where lambdas are the eigenvalues. Okay? So what are we doing? So we're finding that direction V1 is the direction here where the data are most spread out, where their projections are longest onto that direction. V2, if you were to project them all here, the way they're spread out along that direction is as small as possible. Any other pair of directions, the corresponding direction will be shorter, they will not have as large, or they will be longer if we're looking at the orthogonal part. So those are the things that the directions that solve the problem. So the eigenvectors are telling us what direction is that linear subspace that the data lie nearest. And the measure of here, the eigenvalues measuring the projections on the smallest direction, sorry, the direction has the smallest projections, are telling us how close it is. Okay? Okay, picking up from last day, principal components. So we're interested in reducing the dimensionality of the data so that we can actually use some of our visualization methods, which are constrained to small numbers of dimensions effectively. And just go over this very, very quickly from last day. So recall that we can get an orthogonal projection matrix, of course, onto any subspace formed by that very familiar expression there from regression and what we've seen before. So what I want to look for are there directions which when we project the data, so imagine that every data point here in 2D is a vector emanating from the origin. So everything is being centered so that the average has been removed on all dimensions. So imagine each one of these points being a vector, right, emanating from the center. And think about, is there a direction when we project onto the line defined by that direction, the line through the origin, that the projected values will be as large as possible, the squared lengths of the projected values. So if we have x here as this vector, think about any direction vector A, project x, that x vector, onto that direction, that subspace, and then think about two things. What's the squared length of that projection of x onto that? And what's the squared length of this residual vector, the orthogonal piece? Or equivalently, the projection of x onto the orthogonal direction to A. Okay? Everybody get that? So we'd like to find an A that maximizes or minimizes the sum of the squared projections. Whoops. So we know how to project that. And the sum of the squared projections can be expressed as this quadratic form. So the sum of the squared projections of the x's onto the direction vector A looks like A transpose X A, where X is the matrix of the data, where every row is one of the vectors in the d-dimensional space. Or sorry, p-dimensional space. Okay? Everybody with me? So we did that last day. Right? Okay. So what I want to do is maximize that. Subject, find an A, the direction A, find a vector A such that this is as large as possible, subject to the constraint that A has length 1. So I have this constraint. That's this. If the length of A is 1, the Euclidean length of A is 1, then this squared length is 1. So that's A transpose A. And how many people have not seen Lagrange multipliers before? Good. Everybody's seen them before. So that's easy to add that constraint, that equality constraint, simply by adding this Lagrange multiplier times the constraint. So when I differentiate that with respect to lambda and set it equal to 0, I'm going to get 1 must equal A transpose A. So that'll be a set of equations for that, or an equation. So what we have here then is a quadratic form. More generally, it's Z transpose AZ for some symmetric matrix A. And a linear piece. So these are all going to involve Z squareds and ZI, ZJs, cross products. And these are just going to involve constant sums ZIs. And we need to differentiate that. So here, this is our quadratic form there. That's our ZA, Z transpose. But it's also got this piece in here, which has got an identity in between. So our corresponding to A here is going to be X transpose X minus lambda times the identity. Right? So differentiating that, we get a system of equations. And I think we got to all of this last day. So X transpose X A equals lambda A, and that suggests that A must be an eigenvector of the matrix X transpose X, and lambda's corresponding eigenvalue. Okay, any questions? Anyone not seen eigenvectors and eigenvalues? Good. So that should look familiar. You should recognize that as the equation, defining equation of a eigenvector and eigenvalue. Remember, A has length 1 here. So if we think about maximizing this quantity, knowing that A must be an eigenvector, that's just equal to this. And knowing that A must be a direction vector, that equals that. So lambda, that eigenvalue, you now have a geometric interpretation. It's the sum of the squared lengths of the projections of the data onto that direction A. Okay? Any questions? None. So if I want to have that maximized, what do I want to do? I want to find the direction A that is the eigenvector corresponding to the largest eigenvalue. If I want to minimize it, it's going to be the eigenvector corresponding to the smallest eigenvalue. Okay? So putting these all together, and again, if I repeat that process where I'm looking for a new direction that's orthogonal to the ones I've already seen, but maximizes or minimizes, depending which direction I'm coming from, I'll keep peeling off each eigenvector rather, and the eigenvalues. Okay? So that means I've got this eigen-decomposition of this matrix. The symmetric, real symmetric matrix decomposed into the product of the matrix of eigenvectors in the columns, the diagonal matrix of the eigenvalues, and the transpose of the matrix of eigenvectors. And you know, for example, that V transpose V is the identity because they're orthonormal. Okay? So that means these vectors are actually telling me which line, which when I project all of the data on it, the sums of the squared lengths is largest. The eigenvalue is telling me the sum of those squared lengths. So I've automatically got a means of identifying where these data are most spread out linearly, because I'm only looking at linear projections, and or the direction where they're least spread out. Okay. So that suggests that in this particular case, the data points look like they're near that dashed line. And what do we mean by near? Well, we mean the orthogonal distance between the points and that dashed line is pretty small over all of the points. What do we mean by that? Well, by that we mean that the sum of the squared, or the average squared length, same thing, the sum of the squared lengths along the vector that is orthogonal to this one is pretty small. So that when I project all these guys down onto that V2, the sum of the squared lengths is, or the average squared length is small. So if, for example, I threw that V2 away, I haven't lost very much information. They're near that line. Okay? So I'm going to look at these eigenvalues are telling me, am I close to a line? Small eigenvalues are telling me that I've got some directions for which the average squared length of the projection along that direction is pretty small. If that was 0, they'd be exactly on the dashed line. Okay? You often see this expressed in terms of variance-covariance matrices. Is that how you saw it? Don't care about variance-covariance matrices. Just think of the geometry here. We're thinking about orthogonal projections. Okay. And it does show you that variance-covariance matrices are just chasing this kind of structure. Okay, so if I have that, then maybe if I was looking for a new coordinate system, if I had the coordinate system instead of this axis and that axis, E1 and E2, let's say, I had V1 and V2, all the points are going to line up flat along that V1 axis, close to it. So I might consider a change of variables. So every vector x, I look at it in terms of where does it appear on these vectors y, on these new axis system. Okay. So what you want to think about is when I actually write down a vector x in this p-dimensional space, it's telling me the coordinate that goes along with every one of these orthonormal basis vectors. The EIs are defining our axes, our original axes. What I want to do is write that in terms of these y's, which means I've got a different set of basis vectors, different set of axes, and consequently different coordinates. Okay? And so these coordinates, or VV transpose x, are going to give me the actual positions, right? How far along each one of these orthonormal vectors I have to go. So again, back to the picture. If this is x1, x2 in this coordinate system of E1 and E2, it is also equal to y1, y2 down here in the coordinate system of V1 and V2. All right? So I can change coordinate systems, no big deal. When I do that, I've actually chosen these so that the y's, the coordinates, are really spread out, y in the first direction, and they're least spread out in the last direction, in the pth direction. Okay? These guys are language here. These are called the principal axes of the data, and the values, these variables, y1 to yp, the principal components. Okay, and so footnotes here is note that sometimes you'll find both the axes and the variables are called principal components when you look out there in the vast world of the internet and various books and authors. But think about these as the geometry here. I'm picking up the axes and the coordinates. Okay. So the last footnote there is we look back here, the data in this axis system of E1 and E2, that data is correlated, right? A positive correlation that you see there. Large values are associated with large values. In this new coordinate system, the data, the y's, are uncorrelated. So you have to tilt your head on the side and imagine that this axis, and you'll see that, you know, large values in the V1 direction could be large or small values in the V2 direction. They're uncorrelated. Okay? So this transformation, going to these principal components, ends up with uncorrelated values y. So we've taken out that first correlation and we've just removed linear structure. Okay? So remember that a correlation is, for positive correlation, it's chasing, is there an angle here? Are they near a line in that direction? But it's only chasing linear structure. So if we see it looking like this, that's a zero correlation, supposed to be horizontal. But this is also zero correlated, even though there's clearly a relationship. The correlation is only chasing linear structure. Same with these things. Okay? Right. So if I do that transformation, the data is going to look like this. And you see that it's uncorrelated and lies along the principal axes. All right, so if we transfer this, we've got uncorrelated, which means we remove the linear dependency. And that's all. But we've been talking about subspaces. So we're getting down, this looks like the data here, that if you imagine the vectors appearing along, connecting the origin to these dots, these vectors all look like they're very close to lying in this one-dimensional subspace, linear subspace. Okay? Of course, they're all sitting in a two-dimensional space. They're sitting in a plane, but the particular instance of vectors look like they're close to this one-dimensional subspace, which we've identified by the eigenvector v1. Okay? So, some things to note. I think we've already talked about this, that the sums of the squared lengths, right, actually correspond to those lambdas, to the eigenvalues. So each zi here is projecting xi onto the direction vj in this choice. And when I do that and look at the sum of the squared lengths of those projections, just going to be that coordinate, I'm going to find that the sum of the squared projections add up to this lambda j. So that means if in the special case where I actually have that equal to 0, then the data projected along that direction have no length. That is, they really do live in that subspace defined by the other vectors, defined by everything that's orthogonal to Vj. Okay, so when I see that, the data must lie in a space that's orthogonal to that direction. Because when I project on that direction, nobody's there. They all project to 0. Okay? So what becomes interesting is, so that's for any direction. So suppose I could find some collection of directions, right, where all the lambdas are 0 or close to 0. Then I know the data live in the space orthogonal to all those directions. So what am I looking at? I'm going to look at ordering these eigenvalues from largest to smallest. There's going to be some number of them. If some number of them is greater than 0 and the rest are all 0, then I know the data must live in a d-dimensional subspace. Because there are p minus d directions, Vj's, which when I project the data onto that, they all go to 0. Okay? So they all live in some d-dimensional subspace. They all live in a space that's orthogonal to all of those p minus d directions. Make sense? Right? You want to think about, if I've got a direction that everything projected onto it has length 0, then I know the data must live in a space orthogonal to that direction. Because that's the only way I project down to 0, because they're non-zero vectors. Right? If I have some number of those, and they're all orthogonal to each other, well, they all define a space. So I've got p minus d of them, all orthogonal to each other. They define a p minus d basis for a p minus d dimensional subspace. When I project my vector onto any one of them, I get 0. So I project on any linear combination, I get 0. I project onto that space defined by them, I get 0. The data must live in a space that's orthogonal to that space. Okay? So that is to say, if I find that I've got some number of eigenvalues greater than 0, d of them, and the remainder, p minus d, are equal to 0, then the vectors must live in the subspace defined by v1 through vd. Okay? Defined by these principal axes. So the xi's live in that span. All right? If all the data lives in that span, why do I care about the places where the data aren't? So I could reduce the dimensionality of the problem from p dimensions to d. Right? There's no data up in those spaces. Just look at the d-dimensional space. So the next step is, suppose they're not 0, but they're really tiny. The data still occupy the full p-dimensional space, but they're really close to a d-dimensional subspace. Okay, so they're nearly in there. So that means if I throw away all the pieces that are in the p minus d dimensions, in the dimensions where the eigenvalues are close to 0, maybe I haven't lost too much structure in the data. That's the thinking. Okay? Okay, so that's it. So maybe we can reduce this thing to d dimensions if these things are really close to 0. We're clearly losing something, maybe not so much. Okay? So that says if we change to our axis system to the y's, right, which amounted to projecting every one of the x vectors, the same thing of taking the x matrix, when I multiply on the right by the V matrix. That's the same as taking every row in X and projecting it onto those vectors V to get the coordinates. So I can take just the first D columns of these and use that and apply that to X. That's the same as if I used all of them, but only took the first D columns of Y. Okay? All right, so there's a handy decomposition we talked about in the tutorial last day, and that's a singular value decomposition, where I can just operate on the X matrix itself. I don't even have to form X transpose X and get its eigen-decomposition. So the singular value decomposition breaks X. X is a rectangular matrix, n by p. P, n by p, breaks it into the product of three matrices. The first matrix, U, is going to be, the way I'm writing is you see it defined lots of different ways. It's going to be n by p matrix. Its columns are going to be orthonormal. So U transpose U is an identity, P by P identity matrix. Okay. D sigma is a diagonal matrix whose diagonal elements are non-negative and ordered from largest to smallest. And then V transpose, V is going to be a P by P matrix that's orthonormal. So you see that if I have these things are called the singular vectors. They're left singular vectors and right singular vectors. And these sigmas are the singular values. Okay? So the beauty of this is if I take the singular value decomposition of X and then find the matrix X transpose X, so X transpose X, X transpose is going to be, transpose of A, B, C is going to be C transpose B transpose A transpose. Right? That's how the transpose operator works. So this X transpose is going to be V D sigma transpose. That's a symmetric matrix. So that's just D sigma times U transpose. So I get that. And now I just apply these values. U transpose U is orthonormal. So that's the identity. D sigma times D sigma, that's a diagonal matrix multiplying itself. So it's just the diagonal matrix of the squares of the sigma i's. And that looks like our eigen-decomposition. So the singular values are connected to the eigenvalues of X transpose X. Singular values are going to be the square roots of the eigenvalues. Okay? Positive square roots. And if I have the singular value decomposition here, that means I've got the V matrix that I want, the matrix of eigenvectors, so I've got a quick way to get the principal components of the data from the singular value decomposition. Okay, it's just going to be X times V or U D sigma. All right? Okay. So we're going to use the singular value decomposition on the centered X matrix. Okay, so let's do something. So what do I do here? Okay, so in R, we've got looking at the all of acids. I'm going to center it and scale it. And singular value decomposition, often referred to as the SVD, and you just take SVD of the data as we have it, and you can pick off as the components the U, the diagonal, and the V. Okay? And if we look at those, just rounding here, you can just check that V transpose V. So this is the transpose of V, matrix multiply times V, rounded to 10 decimal places. And sure enough, you get an identity matrix. And V transpose, also an identity matrix. Since V is a square matrix with orthonormal columns, it's going to be also have the other way around, you're going to get the identity. V transpose is the inverse of V. And for U, same thing. Transpose of U times U is going to be an identity matrix. Try that. That's not going to be the identity. UU transpose. Okay, so we're only talking about the columns of U. The other thing, the diagonal, you get a diagonal matrix here. Where you can see that the values go from 46 down to 1. So there's quite a difference in the size of the eigenvalues. Okay. Some of these are way bigger than others, and so we might think about, well, which ones, how different are they relatively? And what one often looks at is something that's come to be called a scree plot. I think related to, actually the scree is the bottom stuff at the bottom of a cliff that you see sort of falling down the rocks and things. So it looks kind of like that. So what I've plotted here, just to get a standard comparison, I always plot the diagonal elements divided by the maximum. Okay, so I get a relative size going from 1 down. So these are the axes, the first eigenvalue, the second eigenvalue, third eigenvalue, etc. You see that eventually this is getting quite small compared to this. So this is where most of the data is spread out in this direction, next most in that direction, orthogonal to it, then in that direction, etc. And so we look at this and think about, is there a place, if we cut this off at some place and say only look at the first 4 directions, 4-dimensional data instead of 8, have we lost much? And it said here, ideally it would go along and then it would suddenly drop. Okay? So that's a scree plot. You might look at also at what proportion. So you can think about the singular values, take the singular values, dividing by the, well, let me put it this way. If I look at the eigenvalues here, this direction is the best defined. This is second best defined, third best defined. So if we think of that as being 1, right? This being not quite a full dimension. Maybe the dimension is the sum of these two. Maybe now it's a sum of 3. So the dimensionality in the data, if you allow me the notion of a fractional dimension, I might think about the sum of these various ratios as measuring dimensionality. So I could look at this as this measure here as a measure of the effective dimensionality of the data. And now I'm looking at not the eigenvalues, but the ratio of the singular values. So this is the sum of the ratios of the singular value to the largest singular value. Okay? If the data were in a perfect cloud spread out so that all eigenvalues, all singular values were identical, this would be the dimension of the data. As you compress one direction of that cloud, you've got less evidence that that dimension exists, and so it's only contributing a fraction of a dimension. That's the notion. Okay? Is anybody here taking stat 444? Couple. You recall this in smoothers as effective degrees of freedom. Okay? So we're just looking at the data really are living, if you allow fractional dimensions, they're living, it's a measure of how close they are to smaller dimensional spaces. So what we might look then is at the ratio of the sigma I, add them up, right, as we're going along, or over the proportion is another measure of the dimensionality. So looking at these singular values themselves, adding these up, versus the total sum of the singular values. And so to get the full dimensionality of the data, I have to go all the way up to 8. But maybe ending at 5, I've got most of the dimensionality. It's another way of looking at this and thinking about it. Alternatively, if I looked at the squares of these, and I could think about that as those sum of squared projections are kind of like the variability in that direction. And think about the proportion of the variability in the data that I've summarized by fewer dimensions. So all these things are intertwined, looking at the singular values being the keys. Okay? Secrets to the universe and singular values.